welcome back to my channel. In today's video, we're diving into some interesting problems in calculus, specifically involving limits and improper integrals. These are essential concepts, especially if you're preparing for college level calculus or math heavy subjects. For this item, we're going to verify that the three conditions of Rolle's theorem are satisfied, and we're going to find the value of C that will satisfy the conclusion of the theorem. So, our function is x times the natural logarithm of x on the closed interval 0 and 1. So, the first conditions in a Rolle's theorem is the function is continuous on the closed interval 0 and 1. So if we plug in 0 in the function, we have undefined. So, but however, we can find the limit of the function as x approaches to 0 from the right. So we have 0 because as we plug in any values from the right of 0 is that it is getting closer and closer to 0. So we defined f of 0 is equal to 0 to make f continuous, or the function continuous on that closed interval 0 and 1. Now the second condition is that the function is differentiable on open interval 0 and 1. Now if we derive the function, we have ln x plus 1. X times natural logarithm of x is differentiable on open interval 0 and 1 because its derivative exists and is defined at every point in that interval, because the ln x plus 1 exists for all x greater than 0, including all x element of the open interval 0 and 1. So no sharp corners, no discontinuities, and the derivative is valid throughout the open interval. For the last condition, f of a is equal to f of b. So f of a refers to 0 and b refers to 1. So our f of a is 0. So if f of 0, going back to the limit by definition by limit, so we have f of 0 is equal to 0, and f of 1, if you plug in 1 to the function, we have 0 because ln 1 is 0. So 1 times 0 is 0, so that both the function f of a and f of b is 0, so we can equate the two. So we have f of 0 is equals to f of 1. Now, we satisfy the three conditions of the Rolle's theorem. Let's proceed to finding the value of c that will satisfy the conclusion of the Rolle's theorem. Now, finding c, as the Rolle's theorem says that if the three conditions are met, then there exists at least one value c element of the open interval a and b such that f prime of c is equal to 0. So we're going to equate the derivative of the function into 0. So we have ln x plus 1 is equal to 0. Then transpose the positive 1. So we have ln x equals to negative 1. And finding the value of x is that we have x equals to the Euler's number, or e raised to negative 1. So the explanation for this is that the definition of the natural logarithm shows by this. So ln x equals to y means that x is equal to e raised to y. So the natural logarithm and exponential are just inverse. So we have x is equals to e raised to negative 1, or we can rewrite this as x equals to 1 over e. So the value of c is equal to 1 over e, or approximately 0.36 or 0.3679. So this is the value where the derivative of the function will be equal to 0. As you can see in this scientific calculator, if you plug in 1 over e to the function or the derivative of the function, so this will result to 0, therefore satisfying the Rolle's theorem that if the three conditions are met, then at least one value of c will, if we plug in into the derivative of the function, therefore it will be equate to 0. So we have value 0 as we plug in the c value here. For this item, we're going to evaluate the limit of 2x squared plus 1 all over 4x squared plus x as x approaches to infinity. First, we check if the limit exists through direct substitution. So we substitute infinity to the function, then we get an indeterminate form of infinity over infinity. Since it's indeterminate, we can apply here L'Hopital's rule. So first, we find the derivative of the function 2x squared plus 1 all over 4x squared plus x. So through chain rule, we have 2 multiplied to 2x. So in L'Hopital's rule, we are going to derive the numerator and denominator separately. So for the numerator, we have 2 times 2x, and for the denominator, we have 2 times 4x plus 1. So now, simplifying that, we have 4x for the numerator and 8x plus 1 for the denominator. Since we can simply further simplify this by factoring x. So factor x to the numerator, so we have x times 4, and for the denominator, we have x times 8 plus 1 over x, because 1 over x times x equals to 1. So now we have 4 over 8 plus 1x. So this will be used now in evaluating the limit. So we evaluate the limit of this first derivative of the function. So we have limit of 4 over 8 plus 1 over x as x approaches to infinity is equal to direct substitution. So we have 4 over 8 plus 1 over the value of x, or the infinity, we're going to substitute, so 1 over infinity. And as we all know, 1 over infinity is going to 0. So the limit of 1 over infinity is 0, so we can write this as 0. So we have 4 over 8 plus 0, and 4 all over 8 is 1/2. So the limit exists, and the limit of the function is 1/2. For this item, we're going to determine whether the improper integral negative infinity to positive infinity of 3x divided by the quantity of 3x squared plus 2 raised to the power of 3 with respect to x is convergent or divergent. So first, what is convergent and what is divergent? So convergent, an integral is convergent if it gives a finite or real number as the result, while the divergent integral is if it goes to infinity, negative infinity, or just doesn't settle to a finite number, just like undefined. So now we in this item, we can use the definition, this definition, because this definition is applied to when the boundaries are both infinity. So the definition will be the limit of, so basically the negative infinity here is substitute by a, then the upper boundary will be 0, then just like the other, so now the upper boundary will be substitute to b, and the lower boundary now is the 0. So first we integrate or define the integral of, find the integral of this 3x over 3x squared plus 2 raised to the power of 3 with respect to x. So to find the integral of this, we can use u substitution. So we let u is equals to 3x squared plus 2 because that is our inner function. So now the derivative of u is 6x dx. Now we can use here the value of x dx, since we can see here we have x dx. So if you can find the value of x dx, so x dx is du over 6. Now substitute these we let values. So we have integral of 3 times du over 6 over u raised to 3. Then 3 divided by 6 is 1/2, so we have 1/2 du in the numerator, and to the denominator as same is u raised to 3. So now we can get the reciprocal of the denominator and multiply it to the numerator. So we have the integral of 1/2 times 1 over u raised to 3 with respect to u. So we can get a constant which is 1/2 outside the integral, so 1/2 times the integral of u, 1/2 u raised to 3, or we can write as u raised to -3 du. So now applying a rule for integration, so we add 1 to the exponent of the u, and for the numerator the exponent, and we need to add 1. So now we have 1/2 times u raised to -2 over -2 plus c. Now we have simplifying, we have u raised to -2 over -4, because 2 times -2 is -4. So we have transforming it to getting rid the negative sign in the exponent. So we have -1 over 4 u raised to -2. So substituting back the value of the original value of u, which is 3x squared plus 2. So we have -1 over 4 times 3x squared times the quantity of 3x squared plus 2 raised to the power of 2 plus c. So now we will use this value of the integral we get and substitute this into the definition we use. Now let us evaluate first this part, first part. So we have limit of the integral a to 0 of 3x divided by quantity of 3x squared plus 2 raised to the power of 3 with respect to x as a approaches to -infinity is equal to the limit of the definite integral a to 0 of negative 1 over 4 times the quantity of 3x squared plus 2 raised to the power of 2 as a approaches to negative infinity. So now, applying the definite integral rule, so we have a minus a minus 0, so we substitute a here first and then minus the function which is substituted by the 0 as to the x. We have now, after substituting a and 0, so we have limit of the quantity of negative 1 over 16 plus 1 over 4 times 3a squared plus 2 raised to the power of 2 as a approaches negative infinity, and then applying the limit, so we are left with negative 1 over 16 plus 1 over 4 times the quantity of 3 multiplied to negative infinity raised to 2 plus 2 and raised to the power of 2. So this part is basically 1 over infinity because the denominator is or had infinity, so it will approach to infinity. So basically this denominator will become infinity, and now we have negative 1 over 16 plus 1 over infinity, and 1 over infinity, as we all know, is 0. So we are left with negative 1 over 16. So in this part we just have negative 1 over 16. So moving to the next, which is this one. Now evaluating this limit, so this will become the limit of integral 0 to b of 3x over the quantity of 3x squared plus 2 raised to the power of 3 is equal to the limit of the definite integral 0 to b of negative 1 over 4 times the quantity of 3x squared plus 2 raised to the power of 2 as b approaches to positive infinity. So applying the rule for definite integral, so we substitute the 0 and b and minus the b minus the lower boundary, which is 0. So after substituting the values, we have the limit of the quantity of negative 1 over 4 times 3b squared plus 2 raised to the power of 2 plus 1 over 16 as b approaches to positive infinity. And this one is negative 1 over 4 times this is infinity, so we have just negative 1 over infinity, and the limit of 1 over 16, since it's constant, so the limit of constant is the constant itself, so we have 1 over 16. So as we all know, negative 1 over infinity is 0, so we have 0 here plus 1 over 16, so we just have 1 over 16. So you can replace this as 1 over 16. Since negative 1 over 16 plus 1 over 16 is equal to 0, therefore the conclusion for this is that the improper integral converges, and its value is 0. So since the limit of the integral is equal to 0, the limit of the both limits are results to 0, so therefore the improper integral is convergent and its value is 0. For this item, this is another form of improper integral, and our task is the same. We need to determine whether it is convergent or divergent. So integral of 0 to pi over 2 of tan theta d theta, or with respect to theta. So first, we need to determine what definition we're going to use. So we are going to use this kind of definition. This definition is applied when the upper boundary is if we substitute the upper boundary into the function, it is not continuous. For example, we have this scientific calculator. If we substitute the upper boundary, which is pi over 2, so we have pi over 2, the value of this is, so math error, so it is undefined or something, not continuous. So tan 0 is 0, so it is not continuous at the upper boundary, so we need to apply this kind of definition. So applying this kind of definition, limit of the integral 0 to t, or it depends on you on what variable we're going to use here as representation of your upper boundary, but for this time I'm going to use that letter t. So limit of the integral 0 to t of tan theta d theta as t approaches to pi over 2 from the left. So first, we need to find the integral of tan theta d theta. So if we find the integral of this, we need first to express this into its equivalent, or sine theta over cosine theta, which is just equal to tan theta. It is because we cannot integrate this if it is in this form. So we can apply this process, and then we use u substitution, and we let u as our cosine theta, or we let cosine theta as our u, and the derivative of cosine theta is negative sine theta with respect to theta. So substituting the values, we have integral of negative du. So why negative? Because we have here du as negative sine theta d theta, and we transpose the negative, or multiply both side of the equation to negative 1, so we have negative du over sine theta d theta. So we have negative integral of du over u, and 1 over u. The integral of 1 over u is ln u, as we all know. Now substituting back the value of u, which is cosine theta, so we have negative ln negative 1 times the natural logarithm of the absolute value of cosine theta plus c. As for continuation, so now we substitute the integral we get earlier, so it will now become the limit of the from limit of the integral 0 to t tan theta d theta as t approaches to pi over 2 from the left, it will now become the limit of the quantity 0 to t of negative ln, a natural logarithm of cosine theta. It's absolute value, by the way, as t approaches to pi over 2 from the left. So now we have t minus the 0, so it will now become this. So ln cosine 0 and cosine 0 is equals to 1, so ln 1 will become 0. So this part will stay the same because we're no left to simplify this. So now applying the limit, so the limit of 0 is 0, so we don't write that. And now the limit of this will become negative ln of absolute value of cosine pi over 2. And cosine pi over 2, if we get our calculator, so cosine pi over 2 is 0, so we have negative natural logarithm of 0. So the natural logarithm of 0 is undefined, so we can represent this as infinity. So we have negative infinity. Since this is negative infinity, our conclusion is that the improper integral 0 to pi over 2 tan theta d theta is divergent, since its limit doesn't exist. So for watching, see you on the next video.